Well, hello. How are you today? I hope you are enjoying your day of geometry as much as I certainly am. Today we're going to talk about perpendicular bisectors. This is a segment that is found in lots of places, but we'll talk about them and especially how they are involved with triangles today. You may recall that we had a little bit of this information on our mirror packet a few weeks ago. So, definition of perpendicular bisector. A perpendicular bisector is something that is perpendicular to a segment, that's kind of obvious, and it contains the segment's midpoint. So it bisects it, cuts it into two equal parts. So here's a little example of that. There's our segment. To be a perpendicular bisector, we got to make sure that it is perpendicular and that those two parts are congruent. We'll talk more about this picture in just a little bit. Second term we're going to look at today a little bit is a term that's called equidistant. You may have heard this term before. So again, it's not a real hard term to figure out, but if something is equidistant, then it is the same distance from two or more things. So you might say that a point on the perpendicular bisector is equidistant from the endpoints of that segment, which leads us into a very important theorem today. That theorem is referred to as the perpendicular bisector theorem. Pretty fancy name, I know. Perpendicular bisector theorem says simply, if you are a point on the perpendicular bisector of a segment, then you are equidistant, or the same distance, from the endpoints of the segment that is getting bisected. So I'm giving you a nice little visual here. That point in blue is exactly the same distance from the endpoints of the black segment. So don't just write this down right now, but write it down and attempt to understand exactly what you're writing down. Let it soak in. So that green distance and that green distance should be congruent. So in a few moments, when we are done with all this instruction, one of the problems I'm going to ask you to work on with a partner is to prove this theorem is true. If you will, prove those two green segments are congruent. Now, the other big idea we're going to work on today is talking about a point called the circumcenter. Now, you might recall that the circumcenter is one of the points that you have to find for your project. So this information right now is pretty important. What exactly is the circumcenter, and how does one go about finding it? Well, in a triangle has three perpendicular bisectors. It has a perpendicular bisector for each side of the triangle. We did this in the mirror packet. Well, I'm here to tell you that those three perpendicular bisectors will always intersect each other, and that intersection is referred to as the circumcenter of the triangle. The circumcenter is always the same distance away from all three vertices of the triangle. Might be an important piece of information for you to remember. So here's a little example of what I'm talking about. I've got a triangle here. I'm just going to eyeball right now where the perpendicular bisectors would approximately be at. Well, let's not eyeball. Let's actually go ahead and do some work here. I'm going to put my protractor on here. And again, I am kind of just guessing here a little bit. I'm cheating, I know. You could use a ruler for this right now. What you really should do on your project, use a ruler, find the midpoint of the segment, and once you find that midpoint, put a point there, and then use a protractor to create a 90-degree angle. So here is my first perpendicular bisector, perpendicular to that bottom side of the triangle, and hopefully if I've eyeballed it fairly well, separating that side into two parts. Now I'm going to repeat this process now. I'm going to do it for one of the other sides of the triangle. And just bear with me here as I try to get my protractor to work, being a little temperamental right now. There we go. And I'll turn this thing around and slide it over there. And again, I'm not being overly neat and accurate with where that midpoint is. And it's about there, I'm going to guess, for just the time being. And I am going to roughly sketch in where I think the perpendicular bisector is at. And if you notice, those two perpendicular bisectors do intersect at a point. Of course they do. Any two lines, unless they're parallel, are going to intersect at a point. And now I'm going to go ahead and put the third perpendicular bisector in. And again, I am not being very accurate right now, but for sake of time, I am just trying to get this last perpendicular bisector in the right spot. And if I have done it correctly, I can go ahead and connect these up, and ooh, that was really ugly, but you'll get the idea. Those three perpendicular bisectors all meet right there, and that dark red spot is referred to as the circumcenter. Remember, the circumcenter is the intersection of those perpendicular bisectors, and it is exactly the same distance from that vertice, that vertice, and that vertice. In fact, I could draw a circle that would go through all three of those vertices, and the circumcenter would be the center of that ginormous circle. You could even try it right now if you want to. Now, why does that work? Any ideas? Why is the circumcenter the same distance away from each of the vertices? I would love if you and your partner would figure that out. Come on, you can do it. Put your thinking caps on right now. Figure that out. In a few moments, I am going to give you another problem for you to work on with your partner. And what I want you to do is I want you to draw a couple of different kinds of triangles and discover where the circumcenter will be located in each of those different kinds of triangles. Again, this might be helpful for you as you complete your project sometime between now and the first of the year, and get some points for that. So it's about that time. Let's do a little bit of a partner activity. Alright, find somebody next to you that is roughly in the same spot you are, and let's work on 3 problems right now with them. And I'll give you a few moments here to copy this down, and then I would ask that you would push pause after you copy those things down, work on the problems, and when you are done working, then go ahead and unpause this video and compare your answers with what I have. Yes, of course, you could skip the whole pausing thing and just have me do all the work for you, but then you will get absolutely nothing out of it. And you probably won't do very well on that quiz coming up in the near future. So the first thing we're going to do is do a proof, and we're going to prove that if I have a perpendicular bisector of a segment, that if I choose any point on that segment, that perpendicular bisector, that it is the same distance to the endpoints of the segment. So maybe you'll look at that picture right now and go, that looks like a couple triangles. I wonder how I'll do that. Second problem, as I alluded to earlier, is I would like you to draw an obtuse triangle, I would like you to draw an acute triangle, and I would like you to draw a right triangle. Then I would like you, to the best of your abilities, to draw in a perpendicular bisector for each of the sides of those triangles. So you'll have your 3 perpendicular bisectors of your triangles. And I would like you to discover where the circumcenter is for each of those, making note of that so that when you do your project, you'll be able to know that you're in the right spot. And then perhaps the most important problem for you and your partner to work on, you will have one of these pictures for each of the sections of this chapter. When we work with perpendicular bisectors, angle bisectors, medians, and altitudes, I will give you a drawing like you see here. I will give you information about that drawing and ask you to find a whole bunch of stuff. For example, in this problem, I am going to ask you to solve for x, y, and z, and then find every single length and angle in the problem. So in case you can't see this very well, I'm trying to label that little angle E right now, angle AED, and that's 3z plus 6. And angle A down in the corner, we're going to call that 5z plus 12 degrees. You obviously see the AE and CE down at the bottom are 4x plus 25 and 6x plus 15. And I'm sorry, I'm being a little bit sloppy right here, but hopefully you'll figure it all out. And then for those lengths on the sides, AD is 3y plus 11 and DB is y plus 18. Now the information that you know in this problem is that segment DE perpendicularly bisects segment AB. DE is a perpendicular bisector, so remember what that means. And DE is also a mid-segment of this triangle. So, you got to think back a little bit now. What exactly do you remember about a mid-segment? What are its characteristics? So as I mentioned before, please find A, Y, and Z in all of the lengths and angles. This would be a great time to push pause right now. Alright, now that you've had an opportunity to work on these problems, let's see exactly how you did. In this proof, this is a triangle proof, and so we are going to go about finding the 3 congruent parts that we need to prove the 2 triangles congruent. Since CD is a perpendicular bisector, it bisects the bottom segment, so we know that AD and BD are congruent. Of course, we always remember that things are congruent to themselves, so CD is congruent to CD by the reflexive property. Since we have some perpendicular lines there, step 4, I should say, has angles CDA and CDB both being right angles by definition of perpendicular lines. Of course, we know that if we have right angles, that those right angles will be congruent to each other, because all right angles are congruent. That's going to make our 2 triangles congruent, triangle CDA and triangle CDB, by side angle side. I'll fill in that right angle symbol here in just a second. Remember, if we have 2 congruent triangles, we know all of their parts are congruent, and so that makes segment AC, or CA if you will, and CB congruent by CP/CTC. Since AC and BC are congruent, it really wouldn't matter where C is at. C could be much higher, could be much lower. These 2 triangles are still going to be congruent to each other, and therefore we've just proved the theorem that no matter where you are on that perpendicular bisector, you are equidistant from A and B. Alright, next job. Let's figure out where the perpendicular bisectors will intersect at in an obtuse triangle. your three perpendicular bisectors would look like so. And if you've done it correctly, that circumcenter will be outside of the triangle. Kind of bizarre. Most people wouldn't think of that. If you have an acute triangle, like this one here, and you construct your three perpendicular bisectors, that circumcenter will be inside of the triangle. And lastly, if you have a right triangle and you construct the three perpendicular bisectors, they will land, or they will intersect, directly on the midpoint of the hypotenuse. That is the midpoint of the hypotenuse. And now for our last problem. I've already wrote the three equations here that you should have in this problem. How do I know these things, you ask? Well, I know that since the DE is a mid-segment, then I know that those two parts are congruent. I can solve that and get x equals 5 and find those values. Both of them are 45, so the whole length is 90. Since I know that's also a perpendicular bisector, if it's perpendicular, that means it forms a right angle. That's 90 degrees. So the other two angles might have to add up to 90 degrees. And when I solve that, I get z equals 9. Plugging that back in, I get that angle right there being 57 degrees. And I get that angle right there being 33 degrees. Remember, again, the three angles of that triangle have to add up to 180 degrees. At this point, I can go ahead and find every single angle in the picture. I got a linear pair there, so 180 minus 33 is 147. Obviously, if the one angle is a right angle, then the one immediately next to it is also going to be a right angle. But I'll go ahead and now finish the rest of this problem. Remember, since it's a perpendicular bisector, it bisects that side. Those two parts are equal to each other. I can solve that and get 3.5 for y. When I plug it in, both of those will be 21.5, meaning that whole length would be 43. Now remember, if that's a mid-segment, then those two lines are parallel, and that means I've got a bunch of corresponding angles here. Obviously the two angles next to each other are 90 degrees, but I also have a corresponding angle up at the top, which is 90 degrees. So now in my triangle I have a 90 and I have a 57. So if I add those up and subtract it from 180, I'll know that my last angle is 33 degrees, which, hey, just so you look at it and see it, that's also a corresponding angle to the one over there to the left. So how do you figure out that piece right there? Well, if this is a right triangle, I can use what? That is correct, Pythagorean theorem. And so if I do 43 squared plus something squared equals 90 squared, remember I have to do 90 squared as my hypotenuse, it's the side across from the right angle, I will find out that that starred side is actually 79.1 units. How do I find that question mark now? Well, I could do Pythagorean theorem on the little triangle if I want, or an easier way is to remember the mid-segment is always what? It's always half of the third side. So 79.1 divided by 2 is about 39.5, give or take a little bit. And now I have every length and every side of the triangle. These are the kind of problems you need to be able to do on your next quiz. To get practice of problems that are similar to this, please work on these problems for homework tonight. Page 307, 11 through 21 odd, and 23C. Have a great night.